All right, today is a big day. Today we are going to talk about bivariate relationships. And up to this point, we've been dealing with what I guess could be called univariate um, data. Yeah, univariate data. And we had that univariate data, and we could do things like calculate the mean and the standard deviation of univariate data that we might collect. And from there, we can make assumptions about what our expected value is. Our expected value will always be the mean. And then we can calculate things like the standard deviation that would give us some idea of the spread around that mean that we might expect to see. We could get further and get fancy, and we could think about, well, where do we expect 90% of the data to fall or 95% of future samples to fall and things like that. And then we even took it to the next step where we could use univariate data and we could test hypotheses about it. The means between two groups using a t-test, for example. And so we've been playing around with univariate data, and today I want to talk about bivariate data. And as the name implies, bivariate data has two different things. And so when we think about bivariate data, this is when we're measuring more than, say, one thing from a particular research subject. So it could be, the number of leaves on a plant and maybe the number of fruits on the plant. And we're interested in if there is a bivariate relationship between those two things. And you could come up with all different kinds of examples of things that might be bivariate. And so when we think about describing things that are bivariate, oftentimes what we'll refer to is what's called covariation. And covariation simply describes the tendency for things to rise and to fall together. Or maybe they don't rise and fall together. Maybe one rises and the other falls, or the other one rises and the other one falls. And these are all different ways in which you could imagine a bivariate relationship occurring. And overall, we refer to that as being covariation. And so I'm going to start with, we can start by playing around with just a little bit of the little RE code that we have to play with, because Jim likes playing with R code. And I'm going to start with some data here, and this would be an example of what bivariate data might look like. Here I've measured the length of something, and whatever that something is, I also measured the weight. So, I don't know, you can fill in what it's the length of and what it's the weight of. I didn't really think about a fancy problem to have in the background. But let's say that we've measured this thing. So in total, like what do we have? There's our data. We had 10 subjects. So maybe there were 10 fish or 10 salamanders or 10 trees or 10 ears of corn. I don't know. That would be that'd actually be a pretty small ear of corn. Again, it doesn't matter, Jim. Stay focused. So we have these data, and what we'd like to do is we'd like to describe how they co-vary with one another. We'd like to know that if length goes up, does weight go up? Or if weight goes up, does length go down? We would like to know that. And the first thing that we could do is we could simply plot the data and use the oldest trick in the book, which is use your old noggin and say, what does it look like is happening? So I can just really quickly plot that. Let's look at our data as a plot. And so I eyeball this. Let's go over here. Let's get my fat head out of the way. And so here's our data plotted in this nice little space here. And you can see here's length, here's weight. I could have switched the axes around. At this point, it doesn't matter because all we're interested in doing is describing how the things covary with one another. And so we could eyeball that and say, well, it kind of certainly looks like as length increases, weight increases. Or inversely, as weight increases, length increases, and as they both decrease, and they both decrease together, right? And so we could eyeball that and say, well, it certainly looks like they covary, and they seem to covary in a positive way, meaning that they're both going up at the same time and they're both going down at the same time. So what we'd like to do is we'd like to come up with some kind of maybe less subjective way of describing this relationship. So we would like a numerical or fully objective way at describing how these things covary with one another. And the first step when we start thinking about covariance is we're going to measure and we're going to think about all of these individual little datums here, all of our little data points, and we are going to compare that against a mythical, perfectly average individual. So regardless of what your mentors told you when you were younger, this is a situation where you can't be any better and more perfect than if you are perfectly average. Okay, so this is the perfect average individual. That's what that red dot is. And I cooked up that red dot simply by taking the mean of the length and the mean of the weight, and that's where it fell. And so there it is, right smack dab there in the middle. And so what I'm going to want to do is, the first thing I'm going to do is I want to think about the covariation of all of these individuals from this mythical, perfectly average individual. And I can do that with this little simple piece of arithmetic here. So for any given individual, whatever individual you decide to start with, if I ask how different is that from the mean of all the other individuals for X? And then I could think about that same individual, the second measurement, and how different is that from all the other individuals on that second one. You just take the product between these two. And so for any given subject, you have two different response variables that you have measured from that subject. And if you wanted to know how does that one individual, what kind of covariation is that one individual demonstrating, you would simply just take the product of its value from the mean of the first covariate and its value from the mean of the second covariate. And you take the product of those two, and you would get a measure of covariation for that individual. Now what we'd like to do, going back to our data, is we have more than one data point, right? Because if we just employed this math, that would tell us how different that one individual is from the perfect average individual. But what we'd like to have is a measure of the average amount across all of those different subjects. And so to do that, we would want to take the average of all of those. And this is where things will actually start looking a little bit familiar, hopefully. So here's what I'm talking about. Here I'm taking the sum of all of the deviations of all of those individuals from their respective means on the X or the Y axis. And then I'm going to divide it by n minus 1. And this again should look familiar because that's the same thing that was in the denominator when we calculated variance. And we're doing n minus 1 because we had to understand all of those bivariate points in order to calculate the perfectly average individual. So we have one reference point that we're comparing all these other points to, but the only way that we created that one reference point was to use all the data to calculate where that one reference point is, and so we're losing a degree of freedom. We can think about it that way. We could also think about it the other way of thinking about that n minus 1, which is we know that if we don't do n minus 1, we'll get a biased estimator, and we'll get a biased estimator because all of our observed data will fall closer to our sampling covariation than it is the true population covariation. And then below there, I just showed kind of the other kind of ways that we could pull apart that math, but pretend for a moment that we weren't doing a bivariate thing, and that's when this should look really, really familiar, because this is the same as this, which is the exact same, that is variance. And so we can think about covariation as how things covary in a bivariate sense with two different response variables that we're measuring from those individuals, whereas the variance is simply how something covaries with itself. And that's kind of a way that you can think about it. But you can see here that this, which is covariation, mathematically is super duper similar to this, which is how we calculated the variance. The only difference is here we're dealing with univariate, right? Whereas up here, we're dealing with bivariate. We have both an X and a Y. And so you can see that one one outcome of how this arithmetic is working out is that unlike variance, where we sum, or we took the square, the sum of the squares of all of these, right? Which meant that variance was always going to be a positive number. It's the average amount of spread squared that there is around your central location. Whereas here with covariation, you could easily end up with a negative value. So unlike variance, which is always positive, covariance can be both negative and positive. And I've even made a little mappy here of we can think about it. So here's our x-axis and here's our y-axis, and then our data are going to get thrown there. And so go ahead and we can think about there's two different ways in which you could be positive when you're multiplying those two things together. If you're up in this corner, then you are on the positive side of the mean of x, and in this direction, you're on the positive side of the mean of y. And so a positive times a positive is a positive. Down here in the lower left-hand corner, you have an individual that would fall within this square over here would be less than the population mean for x and less than the population mean for y. And so now you get negative values. A negative times a negative, positive. Okay? And then, of course, if there's two ways to get positive and there's two open squares in there, I bet Jim's going to say that there's two different ways to get negative. Yeah, spoiler alert. Two different ways to get negative. One way is that individuals up in this quadrant here, they are less than the average x, but more than the average value of y. And so negative times a positive, negative. Down in this little corner, down over here, now the individuals over here are greater on the x than the mean of x, but less than the mean of y. So a positive times a negative is a negative. And so now what we're going to do, going back to our formulae, right here, is we're going to simply take all of those, take the sums of all of those products. So you're going to be summing up things that are positive, some are going to be negative, but you're going to be summing them up and then dividing it n-1. We're going to get an overall average, an unbiased average because of the n-1, but we're going to have an overall average of the amount of covariation between x and y. Alrighty, well we're going along really smooth here, I think. Feeling good about this, feeling very good. So let's go back and let's play with R for a second, and let's go ahead and do what Jim just said should and could be done. So the first thing I'll do is I'm going to create an object called length minus mean, because I'm going to take all of my data here for the lengths and I'm going to subtract it from the mean. Hence, length minus mean. When in doubt, make object names easy to interpret. Right? Good. Glad you agree. And then we have weight minus mean. So again, we're going to take all of those individual weights from up here and we are going to subtract it from the mean amount of weight. So I'm going to go ahead and I'm going to do that. Have the computer do some arithmetic. So now I have a vector of, there's all of my length minus means. And again, you can see some of those individuals are negative, some of them are positive. And likewise, we can do the same thing for weight minus mean. Some of them are negative, some of them are positive. And we could go ahead and even look at them side by side. If I had my window the appropriate width, we could. Let's try that again. There we have it. And so here's our raw data. And then for each of these, 64 is 1.5 less than whatever the mean is for the length in centimeters, which by eyeballing this and doing a little arithmetic in my head, I'm guessing is somewhere in the neighborhood of 65.5. But again, you know, it's like, here's an example of an individual that was positive for the length. So that individual, 66 here, that is 0.5 greater than the mean, but it was below the mean when it came to weight. So 141 is clearly 0.8 less than whatever the mean would be, which I'm guessing should be 141.9. And so next, the next part, is we are to remind ourselves, we now have this and we have this. We're going to multiply these two together. And so let's go ahead and we'll do that. And we will call that the product because it is a product, even though I think there's probably a function named product, but just don't tell anyone I did that. So now I'm going to have my products. Okay, so that's the products of those. Again, you can see there's a negative one there, that product. The rest of them, it always seemed to be consistent that if one thing was below the mean, the other thing was below the mean. Or if one thing was above the mean, the other thing was above the mean. But, you know, we got this one oddball here where that wasn't the case, and that's okay. We have all of our products. And now what we're going to want to do is we're going to want to take the sum of all of those products. Okay, sum of the product is going to be the sum of the products. That's the sum of the products, and then we are going to take the average of that, the unbiased average. So we're going to divide it by n minus 1. And so what is the length of our product? And I'm pretty sure it's 10. It is indeed 10. And so once we have that, we can then calculate the covariance. So I'm going to just call it cov. The covariance is going to be what? The covariance is going to be the sum of our product. Sum of our product divided by the length in our product minus 1. And that should give us a measure of covariance. And there it is, 65.5556. All right, we have a measure of covariance. So at this point right now, our covariance is in units of what? Centimeter grams. And centimeter grams can be kind of tricky because what the heck is a centimeter gram? I mean, you could probably get your head around it and think about it. But now let's see what happens if I decided that, you know, since this is America, we're going to do things in inches and pounds, darn it. None of this metric system. It's too confusing with that whole moving of a decimal point. I would much rather deal with whatever the heck this is, right? Okay, great. So now we have our lengths in inches and our weights in pounds. We could plot that out and see what that looks like, and it's going to look just like our previous plot did, right? The only difference is that the units are different. Here we're in inches, here we're in pounds, and then over here we were in centimeters, and here we were in grams. You can see that except for the appearance of that cute red dot, the data are not moving at all, but the units have changed. And so let's go ahead and let's calculate the covariance of that. Now, instead of doing all of this, I always like to do things long once, just so that way at least you will believe me when I say that there's no magic, because I'm always showing you what's behind the curtain. And sometimes I'm telling you whether or not you should switch curtains. But that's the only reason why we did that long, drawn-out thing. Obviously, R is a statistical programming language. Odds are really, really good that there's a built-in function, and there is. It's called cov, which will give us our covariance. So we can even start. Let's go back to our length in centimeters and our length in grams. And do that, and oh, look at that. That's the exact same number we got when we did it by hand. And by hand, of course, I mean we had the computer do it for us. And so let's do the same thing now. And again, it's the same data, it's just in different units. But let's do that with our length in inches and our length in pounds. And now it's that, 0.0568, okay? But now it's in units of inch pounds as opposed to units of centimeter grams. And then you could be really confused if you wanted to, because there's no reason when we're dealing with the imperial system, there's no reason why. No, I don't want to save anything. Go away. Cancel. And so we could, let's do it where we measured the length in centimeters because somebody only had a ruler that had centimeters on it. So frustrating. But, you know, we're going to go back to the old standby pounds because pounds intuitively make so much sense. So now that's the covariance between length and weight, except now it's in units of centimeter pounds. Right. So what should we do about that? Well, this is where our old friend, the Z transformation, will come in handy. Remember, we did the Z transformation when we played with other things, and the Z transformation is simply putting things into units of standard deviations. And that way we eliminate the raw units that we were in, and now everything will be in units of standard deviations. And so let's do that. I don't see why not. Let's do it the longhand way. Z length is going to be what? I'll use that scale function, and I'm going to take the scale of length in centimeters, and then I'll do the same thing for weight, where I will use that cool scale function, and I'm going to take the weight in grams. Okay, so now everything is in units of standard deviation. So that first individual is 0.44 less than 0.44 standard deviations less than the average individual. And in this case, since now we've put it at a standard normal, the average individual will be 0. So let's see, we got that, and let's go ahead and use that cov function. And now we will, stop that. We will, as soon as I get my stuff together here, copy, paste. So now we'll do the covariance on that. And now that's our standardized covariance. And what's really nice about that standardized covariance is that, you know, we could say, well, what if we did have weight in pounds? What's that standardized covariance? It's the same thing. What if our length was in inches? Same thing. How about length in inches, weight in grams? We can mix this all up in crazy sauce town. Look at that. They're all the exact same value, and that's because this is the standardized covariance. And once you have the standardized covariance, now it doesn't matter what units you're measuring things in, because you're going to put them all into units of standard deviations, and we know how to interpret units of standard deviations, and that's going to make us feel great. And so from here on out, we are always going to want to think about the standardized covariance. Standardized covariance is a mouthful, and so I got a better idea. Why don't we call the standardized covariance correlation? That is correlation. Specifically, that is the Pearson product moment correlation. So all correlation is the standardized covariance. And check this out, there's a function that does that, cor. And then I want to have my length in inches and my weight in grams maybe. Look at that. That's our correlation. Correlation is still a pretty big mouthful. Correlation, 4 syllables, whatever, you know, sounds kind of smart. But it's got fewer syllables than standardized covariance. So that's 7 syllables. So let's stick with calling it correlation, since that's what the rest of the world calls it. Except now we know that when we say correlation, in particular the Pearson product moment correlation, what we are saying is standardized covariance. We're understanding how things rise and fall with one another, but now they're going to be in units of standard deviations. So there you have it, standardized covariance, correlation. More in a second. All right, so we should feel excited because now we really have kind of a grasp as to what the heck the correlation actually is. And again, it's just the standardized covariance. We could look at the maths underlying it to see what it looks like. So, you know, that way in case somebody's looking at you over your shoulder, they're like, ooh, you're doing math online. It's impressive. And so here we have, you know, this is our covariance, and then all of this stuff down here is just telling us that we're calculating the standard deviation of x and the standard deviation of y, right? Because we're taking the square root. This would be the variance of x. This is the variance of y. Take the square root of that. It's going to be the standard deviation of both of those. And likewise, we could do it more shorthand and just say, okay, well, we're going to calculate the covariance and then simply divide it by both of the standard deviations. That's going to z-transform it. That's going to put it into our happy place that we want to be in when we're dealing with standardized covariance, or the correlation, as we would like to call it, perhaps, is also called the correlation coefficient, and it's usually shown as a little r, the little letter r. And that's what the correlation coefficient is. And again, to be specific, it's the Pearson product moment correlation. But generally, at least on this planet, when people talk about correlation, usually as a default, they're talking about the Pearson product moment correlation. And then if they're doing something different, that's when they usually add a modifier to it. And so much like, X bar, for example, was our estimate of mu, little r, our correlation coefficient, is an estimate of the unknowable. And it is an estimate of what's called rho. And so rho is the true population correlation. And our estimate of that is little r, is r. Okay? Which means that r is a statistic and rho is the parameter that we're trying to estimate. And so R will measure the strength of the relationship between two variables. If they perfectly covary with one another, then they could have, if they positively perfectly covary with one another, then their correlation would be 1. If they perfectly negatively correlate with one another, meaning that every time one thing increases by one standard deviation, the other thing decreases by exactly one standard deviation, then its value would be -1. So the correlation coefficient itself is constrained between -1 and 1. And again, we have our estimate of rho. That actually is the maximum likelihood estimator for rho, is our little r. And we next might want to think about putting some kind of uncertainty around that estimate. And that's where things can become a little tricky at first, but maybe not. Maybe it'll come pretty easy to you. It's so rho is constrained between -1 and 1. And so now that is a little different than when we were dealing with, say, our estimate of the mean, because we modeled that as a normal, and in principle, a normal goes from -infinity to +infinity. In this case, we know that there's a hard boundary between -1 and 1 for our correlation coefficient. And so if we wanted to do some estimates on it, like the uncertainty around that, we would like to use a distribution that is comfortable to us, that we're familiar with, that we feel good about exploiting, like the normal distribution, for example. But the problem is that our estimate of rho is usually not going to be normal because it's bounded by -1 and 1. And it turns out that if you have a correlation coefficient that's in the neighborhood of 0, like maybe -3, -4 to +3, +0.3, 0.4, maybe you could get away with modeling it as a normal and not be that far off from the correct or the true answer. But once you start having correlations that are closer to -1 or closer to +1, you end up with a distribution that's not only highly skewed, but it's also it's bounded. And so if we want to play around with our correlation coefficient and think about how we're going to go about doing this, what we first would maybe want to do is think about, well, how can we turn R into units that we can use so that we can use the familiar normal distribution. We love the normal distribution. We know how to use it. We know how to calculate 95% confidence intervals. We know how to do hypothesis testing. How the heck do we make this thing normal? And it turns out that there is a transformation that people do, that you can do, not people, I guess you're people, so we're all people. We all can do it. It's called the Fischers RZ Transformation. And the Fischers RZ Transformation was developed by a guy named Fischer, R.A. Fischer. And what it does is it takes R and it converts it into Z units, which are standard normal units. Hence, Fischers RZ. They let him get ownership over it, and it's taking the R and turning it into a Z. And this piece of arithmetic is just simply 1 plus R divided by 1 minus R. You take the natural log of that, you multiply it by 0.5, and now your R is no longer in units of, units of what? Rho, whatever those are, the standardized covariance units. But now we can model directly our correlation coefficients as being random variables drawn from a normal distribution. And once we have that Fischers RZ transformation, we can also calculate the standard deviation around our estimate of rho. And we calculate that through this little piece of arithmetic. And so here's our Fischers RZ estimate of the standard deviation around rho. And it's simply the square root of 1 divided by n minus 3. Okay? Which means that you cannot have a sample size that is 3 or fewer and calculate a standard error from a correlation, for a correlation. So you need to have greater than 3 observations if you ever really want to do any kind of estimate around the uncertainty of your correlation coefficient. So, okay, and then once we have that, so once we have our estimate of the standard deviation of our transformed correlation coefficient, and we have our correlation coefficient in these Fischers RZ units, we can calculate the 95% confidence intervals how we've done in the past when we were dealing with a normal distribution. And so here we will take any of our given values of R, right? Our given value of R after we've done our Fischers RZ transformation, and we're going to take the standard deviation of that estimate, multiply it by 1.96. Actually, it would be 1.955, whatever it is. It's that magic number that is the 0.025 and the 0.975 quantile of a standard normal. And this will give us what our 95% confidence interval is around for our estimate of rho. And so once we do that arithmetic, now we need to back transform it. And because previously when we were here, this is all in Fischers RZ units. But we don't want to talk to people about Fischers RZ units. We want to say, hey, I got this correlation at 0.86. What the heck? How do I do that? And so you take the Fischers R to Z transformation. Once you have that Fischers R to Z transformation and you've calculated what the standard error is around your Z transformed correlation coefficient, just plop it into this formula and you can come up with the 95% confidence interval around your estimate of your Fischers R to Z. But now we need to back transform it back into R units, which are right here, okay? And so it's e to the 2 to the z minus 1 plus 1. If you look at the maths, if you look at that math, that math right there that I'm pointing at ever so intently, see that math? Once I've converted something into z, I should be able to convert it back into r, which I can do by doing that, okay? And so this is another example, and this is, I talked about this when it came to just transforming any data that we were talking about transforming, the importance of back transforming it to communicate to people in the original units if you want to. when we talk about correlations, because they are the standardized covariance, we know exactly what those numbers between -1 and 1 mean. We can visualize in our head what that correlation might look like. And so we're going to want to communicate our 95% confidence interval in the units of Pearson product moment correlation. We're not going to want to do it in Fischers RZ, and so we're going to want to back transform it from there. And so let's go ahead and let's jump back in to R. Right, so now we're back in R, and again, wow, how many times have I written 0.84? I was so excited about that standardized covariance stuff. But here's our correlation, okay? 0.8436. And so let's just go ahead and let's create an object called R, because we're using R. Why not create an object called R? So that's going to be our Pearson product moment correlation, and then our n is equal to 10. We have 10 observations. And so the first thing that we're going to want to do is we are going to want to do that Fischers RZ transformation, which again is that. Okay, so we are going to take 0.5 times the log of 1 plus r divided by 1 minus r. And I'm going to call that object z, because now we're going to be in z land. We have done our Fischers RZ transformation, and now we are in z land. And that's what it is in z land, 1.233674. Again, if the next thing we're going to need to do is calculate our standard deviation, which again, that's the math. So it's just simply going to be the square root of 1 divided by 10 minus 3. And so I'm going to call that sigma z. Sigma z is going to get what? It's going to get the square root, and then, you know, making sure that my order of operations are going to behave. I put the n minus 3 in parentheses down there. But that is going to give me my standard deviation. So that's my standard deviation around this. And again, we are currently living in a universe where everybody talks to one another in Fischers R to Z units. And so now I can use our familiar maths for thinking about the 95% confidence interval. So the upper limit is going to be z plus our estimate of the standard deviation times 1.96. And I'm just using the back of the envelope one instead of that 1.95 whatever for an infinite number of digits. So this is a back of the envelope calculation. So I have an upper and I have a lower. And so again, here's my z is 1.233674, and then I have an upper limit and I have a lower limit. That upper and lower limit are nice and symmetrical around the central part here, which is our Fischers R to Z. And so now we have these values, and we feel good about these values. We have done 95% confidence interval around our Z transform stuff, but we don't want to talk about it in Z. I want to talk about it in R, darn it. And so now let's go ahead and we'll back transform. And so I'm gonna call this capital R just so we can keep track, right? Because I don't want to overwrite this because I'm so thrilled about this correlation of 0.84. I want to find some way to make that object permanent in my computer forever. I'm so happy with it. But what we're going to do is we're going to back transform it. And so just to remind us, I'll pull that little thingy-majiggy up here again and just remind you what we're doing. Right? This is the back transformation from Fischers R to Z units. And so I just typed in that math right here. And it almost looks, I don't know if this looks more impressively difficult or if this does. I guess if nobody's written computer code, that just looks like magic goo. But okay, so we have that. And where is my unexpected, oh, you're killing me. Oh, I see what the problem is. Look what I've done. There we have it. Okay, so that's my back transformed, and then it's always nice to double check. That's why I didn't overwrite it, just in case. You know, it's easy to screw these things up, maybe, you know, parenthesis in the wrong place. But the fact that we successfully took our original R here, we transformed it to Fischers R to Z, and then we back transformed that, and we got that same answer. That tells me that all of the little mathy maths we did here in the computer land are spot on. And so we'll back transform our upper and lower. So I'm just taking our upper Z level and our lower z level, and I'm just popping it into this same little formula here. And so now what do we have? We have, that's our correlation. Our 95% confidence interval is defined by, on the upper bound, 0.962, and on the lower bound by 0.456. And so we are 95% confident that the true population rho falls between 0.45 and 0.96. Our point estimate is 0.84. Right, feeling good. Yeah, I want to point out one thing that sometimes throws people, because when you remember when we were talking about the 95% confidence interval for the mean, when we were using the standard error, which was our estimate around our estimate of the mean, we decided that it was best to use the t-distribution for calculating 95% confidence intervals to account for our increased uncertainty. So we would use the t-distribution, which would give us nice big fat shoulders, and it would allow us to have a lot more uncertainty as a function of sample size. Here we don't do that because Fischers RZ Transformation quite literally turns these numbers into random variates drawn from a standard normal distribution. So we do not need to use a t-distribution in this case. We're totally happy using normal, and we like normal. Just like we like being perfectly average, we also like being perfectly normal. I believe this is what they refer to as indoctrination in universities. I'm trying to convince everybody that they want to be normal and perfectly average. Or at least if we're going to analyze data, that's kind of our reference point that we want to use. And so with this 95% confidence interval, we can easily ask R to give us this. And R will give us this because not only is there this function called core, right, which gave us the correlation, there is also a function called core.test. And core.test will give us the 95% confidence interval. We got the same values, and there's our same correlation. And so now we know where these numbers are coming from, and we understand how that 95% confidence interval is being described. So again, we have to go into Fischers RZ land if we want to calculate that 95% confidence interval, because if we just used a standard normal distribution with our estimate of rho, with our correlation coefficient, it would be entirely easily believable that we might end up with a 95 confidence interval that either is greater than 1 or greater than negative or less than -1. And we know that that's not possible because correlations have to be bounded by -1 and 1. So behind the scenes, we're always going to be doing the Fischers RZ transformation. And it's worth knowing how to do it because it might come in handy in your own work, or when you need to calculate a weird interval that maybe you'll find that it's just easier to do it that way than to hunt down and try to find a function that'll do it. So okay, now we know how to do confidence intervals. So the next thing that we'll do is think about hypothesis testing. All right, hypothesis testing, because everybody loves a good hypothesis, especially if you watch the p-value lecture. So to test hypotheses regarding the correlation coefficient, the usual null hypothesis is that the correlation coefficient is not different from 0, meaning that you cannot reject, or the null hypothesis is that rho is 0, and then the alternative hypothesis is that rho is not 0. Okay, and so that's kind of a standard way that we would set up hypothesis testing. And so what will we use? So for the correlation, to do statistical hypothesis testing, we can go back to our old friend that hung out at the Guinness Brewery for a long time, which is the t-distribution. and we can test hypotheses about the correlation using a t-test. So I mentioned when I introduced t-tests that it's kind of weird that these are called t-tests, because what are these other things called that use the t-distribution? They're all called t-tests, darn it. And so we're going to use a t-test to test the hypothesis about our correlation coefficient. And so let me make myself small again, because I have some serious issues apparently, dysphoria of sorts. We're going to calculate our t-statistic very similarly to how we have calculated t-statistics before. We have our observed value, so our observed estimate of the correlation coefficient, minus some hypothesized value. And again, usually the hypothesized value is 0, but it doesn't necessarily have to be 0. And I'm almost certain that on the homework, I will probably ask whether or not you can reject the null hypothesis that a correlation is different from some other value other than 0. Okay, so it's worth understanding how you can calculate this t-statistic so you can do things like that yourself. And there's a lot of cases where that is very relevant in research. If there's a whole body of theory that predicts a particular correlation and you collect more data, why are you testing a hypothesis that it's different from 0 if you're really doing the study to see whether or not your system agrees with some theoretical expectation? So theta can be whatever it wants. By default, it's usually 0. And then here in the denominator, we have our standard error of the correlation coefficient. And we can calculate the standard error of the correlation coefficient simply with this little piece of arithmetic. So it's 1 minus the r squared divided by n minus 2, and then you take the square root of all that, and that is going to give you your standard error. And so now, unlike when we were calculating the covariance, now we're dealing with correlation, standardized covariance, and we have that n minus 2 in the denominator because we needed to actually calculate two means in order to calculate the correlation. So ignore the top part where we were thinking about all the little kind of ways in which individuals covary against the hypothetical perfectly averaged individual. Here, the two means that I'm thinking about are in the denominator. Remember that we had to calculate standard deviation for x. That's going to ding us 1 degree of freedom. The standard deviation for y, that's going to ding us another degree of freedom. So it's n minus 2 random variables that we have because we went that extra step, decided that we loved Pearson product moment correlation, and we calculated 2 standard deviations. So we had to estimate 2 additional parameters in order to do that. And that's why that n minus 2 is down there. And then once we have that, all we would do is we will pop that right into this formula, and we will be able to play with our hypothesis testing just like we've done with any other t-test that we have done. And so I'm going to go ahead and I'm going to do that in R because I like doing everything in R. And as I said, I like doing everything the really long, slow way the first time. So that way I feel really confident that I know exactly what my computer is doing behind the scenes. Boop, boop, boop. That kind of stuff. And so here I have the standard error of R. And again, I'm calculating that using this formula right here. Yeah, it's right there, right? So here's the square root, the big square root. And then in this parentheses right here, I have 1 minus the correlation of that squared, which is right there. That is the numerator, divided by the denominator, which is 10 minus 2. Okay, so that's going to give me my standard error around R. And there it is, feeling good. And so now I should be able to pop that into this, right? I'm going to calculate my t-statistic. T is going to equal R minus theta divided by the standard error. And so let's say t-stat it'll get what? Well, I will start with my correlation between the weight in grams And the length in centimeters wouldn't matter again. I could have said length in inches because we're dealing with correlations. Everything is standardized in units of standard deviation. I'm going to take that correlation. I'm going to be explicit, and I'm going to say minus 0, because that's my theta, right? That's not going to do anything, but I'm just being very explicit that that is my hypothesized value. It's 0. And I'm going to divide that by the standard error of R. And so I do that. Now I have my t statistic. So I have a t statistic, and I know how many degrees of freedom I have, because I'm going to lose 2 degrees of freedom. And you can already see where this is going because it's already up here. There's the t statistic that we got when we used that core test function just to prove to ourselves that we know how to get the 95% confidence interval. Well, it also gave us a t, and that's where it got that t. Degrees of freedom is 8 because it's going to be n minus 2, because to calculate the correlation, you needed 2 standard deviations. You're just going to start docking yourself some random variables. And, well, how do we get that p-value? So let's see here. We could start with cumulative distribution function of a t distribution, and we're going to say t dot stat is our value, right? The one that we did here. Our degrees of freedom will equal 8. And then I'm going to go ahead and say lower tail equals false. And I do that. But now let's remind ourselves about the tailedness, right? Right now, all we've asked is what is the probability of getting something that great or greater, but we haven't accounted for the fact that because of how we're testing this null hypothesis, we could have been negatively different from 0, right? We know from our correlation coefficient, which is 0.84, that we're on the positive side. And so this right here would give us what's called a one-tailed test. We want to have a two-tailed test because of how we have worded our null hypothesis. Our null hypothesis is that it was equal to 0. Our alternative is that it's different from 0. So we'll multiply that by 2, and that is our p-value. And that is the same p-value that the core test function gave us. So that should be satisfying. It's like, aha. And so if we're going to do deductive type approaches with looking at p-values and looking at falsifying hypotheses, we would say we are rejecting the null hypothesis that rho is equal to 0 and accepting the alternative that rho is not equal to 0. It is different from 0, and either in the positive direction or the negative direction, because it's a two-tailed test. All right. That's it. I told you this stuff was going to start going faster. So all of this stuff all of the output you get from this should not be mysterious at all, because we did it all by hand just now. The only tricky part that is a curveball sometimes is that whole Fischers RZ transformation. It's the kind of thing where you probably won't have to do that by hand often, but there might be situations where you might actually want to do it on purpose. For example, let's say that your response variable was a bunch of correlation coefficients. Let's say you had 100 correlation coefficients from a bunch of different studies, and you wanted to do a t-test or something like that on those correlation coefficients. Well, you would need to Fischer RZ them, then do your statistical hypothesis testing, and then transfer them back. So there are situations at some point in your journey through stats, as it were, where you might actually be really interested in doing that Fischers RZ transformation. Again, as long as you know that it's called Fischers RZ transformation, you can always look it up. You don't need to memorize stuff like that. The only reason why I know it is because I've taught this class a bunch of times, but otherwise there's no way that I would remember that. That's pretty esoteric. But it's important to know that it's not magic, and that's how the computer is coming up with those intervals. Also, it's important to remember that we're losing 2 degrees of freedom with correlation because of the two means and the standard deviations that were used to create the Pearson product moment correlation. And then again, it's always important to remember that p-values are a guide. They are not they don't get the last word. We do not let them get the last word. Right. And so that's that. Oh, I guess one other thing is, again, with my hypothetical example, right? Like, let's say that whatever this was, length and width, let's say that there's a whole body of literature out there, and, you know, some old dude with a long gray beard said, the correlation shall be 0.78 from this point forward. And you collected your data, and you're like, well, I didn't get 0.78. I got 0.84. You might be interested in knowing whether or not 0.84 is different from 0.78. And you might be interested in doing an actual hypothesis test on that. And we can do that. Going back up to our t-stat, and this is where it's helpful to understand how we're deriving our t-statistics. The hypothesized value, what did I say? Oh gosh, 0.78. Okay. And now let's see what the p-value is. 0.74. So I would not reject the hypothesis that this is different from, or is the same as 0.78. Okay, that is an example of where it's important to understand how these t-statistics are actually being generated, so that way you can test hypotheses other than the boring one, which is it different from 0? And that was a little disparaging. I probably shouldn't say the boring one, but maybe the obvious one. Maybe you're doing something creative and you don't want to test the obvious hypothesis. And so it's important to understand how those t-statistics are made. And it's a really powerful tool. We'll revisit t-statistics again with linear models. And again, all t-statistics are pretty much generated the same way. Your observed value minus a hypothesized value divided by the uncertainty around that observed value. That's a t-statistic. So, okay, we're cranking. Alrighty, not done yet, because as we talked about, it is super important to make sure you have some kind of a clue about what kind of power you might have to say anything, especially if you decide that you are going to accept the null or fail to reject the null. Gotta be careful. Even I gotta be careful. You're never accepting a null. You are failing to reject it. And so to do a power analysis on correlations, it's actually quite easy. And you could do a power analysis, a fun exercise, well, fun in a nerdy way, exercise that I have had students do in the past was, I gave them a couple of scientific papers where they were making hay about, failure to reject the null, and there is no correlation between these two things. And nowhere in these papers did they ever mention power. Because again, if you are not rejecting the null and you want to tell a story about not rejecting the null, you sure as the heck better tell people what power you actually had to detect anything. And so with power analyses on correlations, it's pretty easy because all you need to know is the sample size, which papers will always communicate. And you need to know the correlation, which obviously the paper is communicating, because how else would you know that they had a value, right? And so to do a power analysis, we are going to use the library PWR once again. Again, warning message means nothing. It is dead to me. And so the function that we'll use is pwr.r.test. And that's just telling me that we're doing a power analysis on a correlation. So what's the arguments here? I'm going to just look right up above me here. What are the arguments? N. I had 10 observations. What is my correlation? It was 0.8436. That's probably close enough for rock and roll. Significance level is 0.05. That's all good. And I'm not going to give it power, because I want it to solve for power. I guess I will just be explicit for our purposes here and just retype all of that. No, false. What am I doing? Maybe I shouldn't have done anything. I was on a roll. And so I'm gonna have it solve for power. Now, one thing that's different from when we were playing around with power analyses with t-testing is that with t-testing, we had to provide it the uncertainty, right? The error. We don't have to do that here because we've given the function our sample size and we've given our function the correlation. And as we just did a couple of minutes ago, if we have those two pieces of information, we can easily calculate the standard deviation, which is what R is doing behind the scenes. So all it needs is sample size, correlation, significance level. So I'll go ahead and I'll do that. And look at that. I got really, really good power. And of course I have really, really good power. I had a really, really big effect size. The big effect size, it was a pretty strong correlation. That's a high correlation, 0.84. It still means that I would expect to miss it about 8% of the time. Even though the underlying distribution in this population has this really strong correlation where length and weight covary with one another, I still expect to miss it by chance, just by chance alone, about 8% of the time. But I got some pretty good power. And again, you generally always will have really, really good power if your p-value is small enough that you've rejected the null hypothesis. And so, yeah, that's pretty good. But you could imagine, well, what happens if you read a paper? Let's say hypothetically you read a paper and they had 50 samples and they had a correlation of 0.2. And let's say that they did this analysis. They had 50 observations, they plotted it out, they did a nice correlation, and they failed to reject the null hypothesis. And so what kind of power? If they're going to go off and talk for the next 2 pages in esoteric science land about their research, and their whole argument is based upon the fact that they failed to detect that correlation, they should at least present the power. And what kind of power do they have here? Well, they have really, really low power. So you can't really feel that good about, yeah, we failed to reject the null, with the caveat that our power was really, really crummy. And then obviously, as sample size would increase, you would have more and more power, right? So the same kind of rules apply that it applied before when we played around with power analyses. Now let's pretend we had 500 observations. Now we have ridiculous power, and we're going to detect that. It's also another situation where it's important to remind yourself that, is the effect size relevant? In your system, do you even necessarily care about if something covaries at 0.2? That might not be biologically relevant. And so those are always the things that you need to include. So in the not handout, but in the notes that I put up there, I go through all the different power curves again, just like we did with the t-distribution, just to remind you of like the relationship between power and sample size and effect size and significance level, just to kind of remind you of that, because it's a really good habit to get into, to at least be aware of your power. Doesn't mean that you always have to go off on it. It's like, yeah, you don't have to present your power with every single statistical analysis you ever do, although there's nothing wrong with that if you want to. But it's always important in the back of your head to be aware of what your power actually is. And that's true whether or not it's significant or not, because again, when we set that threshold at 0.05, we are striving to be wrong 5% of the time. And it's really important, even if it's significant, it's really important to be aware of what your power is. So yeah, that's power analysis. And next we'll talk about different types of correlation. All right, what I want to do is I want to mention 2 other types of correlation. So as I said, that generally when people say correlation, the whole universe of stats people will assume that you are talking about the Pearson product moment correlation, right? The standardized covariance. But there are 2 other somewhat commonly used types of correlation that I wanted to mention. The first one is what's called Spearman's correlation. And it's also called the Spearman rank correlation. And this is a non-parametric correlation, which means that it's not going to make any assumptions that the mean has to mean what you think the mean means, etc. And the Spearman rank correlation is simply this. It is the Pearson product moment correlation on your rank transform data. And remember, rank transformations, it's the nuclear option because you can never back transform from a rank. But what all the Spearman rank correlation is a rank transformed Pearson product moment correlation. And we can prove that to ourselves, shall we? Using R. So what are where is our silly stuff here? Correlation. So within correlation, there are arguments. One of those arguments is called method. So you can see, and watch me point. So, like that. So Pearson is the default. Pearson is our Pearson product moment correlation. But then you'll see that there's two others up there. And one of them is Spearman. We'll get to Kendall in a minute. One of them is Spearman. So the Spearman, if you wanted to use that, you would just say method equals Spearman. And that is our Spearman correlation, also called Spearman's rho, which is unfortunate because the general rule of thumb, if you remember, is Greek letters are parameters. Our statistics are in normal letters, or however we want to describe them. This isn't the case with Spearman, just out of tradition. They call it Spearman's rho. This will give us the exact same answer as if we had simply just said, well, got to employ the nuclear option. I'm going to rank transform my data because I love throwing away information so much. And we get the exact same answer. So Spearman rank correlation is the Pearson product moment correlation on ranks. And in some older books on nonparametric statistics, they had very convoluted ways of calculating it, and you end up getting the exact same freaking answer if you just rank transform your data and then do a Pearson product moment correlation on it. Of all the nonparametric tests, Spearman rank is probably the most common one that we still see in the literature a lot. And people just feel more comfortable doing that if their data are clearly not a bivariate normal distribution, especially if it's weird bimodality and stuff like that. So, but that's all it is. So all the mystery is gone now with Spearman. If you understand Pearson's, you understand Spearman, you just know that Spearman is Pearson's, but you have done the nuclear option by exploding things. The second one that came up there is what's called Kendalls tau. Kendalls tau. Look at that. I think I will put a, okay. Kendalls tau. And Kendalls tau isn't truly a measure of covariation. I mean, Spearman's is weird enough because you're in rank units, which you can never go back from. But the math underlying it is the same. It's just you're doing Pearson product moment on rank transform data. Kendall's is a bit different. A Kendall correlation is better to be thought of as a measure of concordance. And the easiest way to describe what I mean by concordance is when you have things that are inherently ranks within themselves. And so here's my storybook example so we can understand what the heck Jim's talking about when he's talking about concordance. And the example that I have is, let's pretend that we are interested in ranking beer. Okay? And so we've gone to two different places and we've asked people to rank beers from 1 to 12. So as a disclaimer, I'm in no way encouraging people to drink beer at all. I'm pretending hypothetically that you got a job working for somebody and one of the contract jobs that they had was maybe the distributor wanted to know whether or not maybe X is a bar and Y is a bar, whatever it might be. You want to know if they generally seem to like the same beers at both places. And so you go to both of these places. You go to place X and you go to place Y, and you ask them to rank these 12 different beverages, okay, from their favorite to their least favorite. And so these are inherently ranked, right? I mean, they are not random variables drawn from any kind of a distribution. They are inherently ranked. You had to choose, like, this is my favorite, this is my second favorite, my third favorite, so on and so forth there, right? And so what we mean by concordance is how well do those ranks match up? I mean, I could have done the same if, you know, if we said, well, here's 12 movies that maybe everyone has seen, and you have to rank them from your favorite to your least favorite, or, you know, songs, most favorite to least favorite. Anything that's inherently ranked is appropriate for Kendall's correlation. And again, instead of really thinking about how well correlated those two rankings are, really what we're interested in is how concordant are they. And so we measure concordance with Kendall's tau using this little piece of arithmetic here. So Kendall's tau equals the number of concordant pairs that we have in those two columns minus the number of discordant pairs divided by the number of concordant pairs plus the number of discordant pairs. Okay, so the arithmetic underlying Kendall's tau is super straightforward and really super easy. Understanding what the heck you mean, or what I mean, by concordant and discordant, maybe that is not immediately intuitively obvious. So let's do that. Let's work on that. All right. So we start at the top here, okay? And population A, bar A, sampler A, whatever it might be, gave beer A its number one ranking. The other person gave beer A its number two ranking. And so now let's go through and let's think about what we mean by concordance and discordance. So for the first one here, what we can ask is, given the fact that this person right here ranked beer A number one, now we'll compare it to what person two did. And when we think about concordant pairs, we are asking how many larger ranks are going to be below that particular rank. So in regards to X, this gets number one. And now what we're going to do is we're going to count up the number of ranks below here that are greater than one. And that's going to be our measure of concordance. And so in this case, we start with 1. 2 is not greater than 1. 1 is not greater than 1. But 4 is. 3 is. 6 is. 5 is. 8 is. 7 is. 10 is. 9 is. 12 is. And 11 is. 10. So what we would say is we would say, okay, well, for our first concordant pair, we had 10. And then let's create a vector called discordant. And now with discordant, we are going to ask how many smaller ranks are below a particular rank. So we go over to here, and where do we find there's our discordance. Okay, and so this is why we will have one discordant variable here, because 1 is clearly less than 2. You can ignore the tie. And so for our first one, we are going to say that there is one discordant. So now we go to the next beer. Okay, so this one was number 2 for group X. And then we're going to calculate the concordance the same way. All right, so we go over to here, and we're looking for ranks that are above this now. below here. Okay, we're not hopping back up here, we're looking below here. So we count again, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So for the second one, it's going to get 10. And now we're going to look at the number of discordant ones. And the number of discordant ones below there are 0. There are no values here, all the way down below this row. There are absolutely no values that are discordant. They're all higher than that value. And so, 0. And then we could go through and do the exact same thing the second time, or the third time. Go through here, look at the number of concordant pairs. It starts at 6. 1, 2, 3, 4, 5, 6, 7, 8. That's going to give us 8. And then we could also look at the number of discordant, and there's going to be 1, because 4 is greater than 3, just like 2 was greater than 1, but here 1 was not greater than 2. So there is going to be 1 discordant pair. And so we would go through all of those, and I will go ahead and I will just cut and paste because I already did it all by hand. Okay. I'm only including these NAs, so that way it'll be the same length as all of our data, basically. Because for this last guy here, this 12th guy here, there's nothing below that, and so that ends up not having a value. And so we can look then at what do all of our data look like. Where is that, Jim? Here we have it. So again, here we have our concordance, 10, 10, 8, 8, 6, 6, 4, 4, 2, 2, 0, NA, and then with our discordance, it's, every other one is how I've cooked it up. And then again, there's nothing for the bottom one because there's no rows below it to compare it to. And so we can't have any concordance beyond the lowest level. And so we leave those. And so if we were to then pop that into that equation for Kendall's tau, right? Concordant pairs minus discordant pairs divided by concordant pairs plus discordant pairs. So we would say tau is going to get what? It's going to get the sum of concordant minus the sum of discordant, and we're going to take all of that and divide it by the sum of concordant plus the sum of discordant. Oops, discordant. Okay, so all I've done is I've just typed in that math. So that should give me my tau. Oh wait, I got to get rid of those NAs. Messing with myself. That was just for graphical purposes, Jim. Okay, so now I have a tau. That is my estimate of tau. And then if I were to go ahead and do the exact same thing where I said core.test, and I want to do it between, what did I call these things? X and Y, and method equals Kendall. There's where we get, there's our test statistic that we got here. This is one of the very few times in this entire course where I'm going to say, ignore the test statistic for this. It's not really that important and relevant. But there's our p-value if we wanted to do hypothesis testing. So we would say that there is significant concordance between those two. And we would probably get very similar answers if we had just done a Pearson product moment on it. But again, Pearson product moment is assuming that the data are bivariate normal, and these were recorded as ranks. We asked people to rank 1 through 12, these 12 things. And so there's the correlation we would get with the Pearson product moment. And then some people might argue, well, since you're analyzing ranks, you should probably use a rank-based method, which they wouldn't be wrong. Spearman. And that's what we would get with Spearman. So we have a bunch of different flavors that we could choose to do. Interestingly, note that the Spearman and the Pearson product moment are identical, and that's because we're analyzing ranks. It's already been rank transformed, so it's going to give us the exact same answer. But you can see that Kendall is a little bit, where is Kendall? Kendall is a little bit lower. Any of these approaches would be fine. It's just you should be aware of what you're using and why you're using it. That's especially true with Kendall. There's a couple of disciplines where people have started using Kendall again, and I'm not sure why, but it's not necessarily wrong. The most interpretable of all of them is going to be the Pearson product moment, because it's in that whole body of theory about the normal distribution and understanding that, whereas you don't really have that with Kendall's tau, for example. We're not getting any kind of error estimate around that or confidence around that. We're just getting a p-value. And, we could look at, what did I do? What else did I do up here? What other fun stuff did I do? Oh, I did one where I have perfect concordance. And so here we have a situation where we have perfect concordance. And if we were to do the core.test on that, x and y method equals Kendall, right? We get a correlation of 1. And if they were the exact opposite of one another, so if I were to say, let's reverse a function. It is. Sweet. So if I were to reverse y, would that? I would. How handy. So let's say that y were the reverse of that. Now it's a negative 1. So just like with Pearson product moment and with Spearman, the coefficient, the correlation coefficient, is going to be constrained between -1 and 1. But with Kendall's, it's handy to keep into your mind that that it's not truly a correlation. It's a measure of concordance. Are things matching well, or are they not matching well? Which is different than thinking about, are things covarying or not covarying. And then the last one that I kind of cooked up to play with is an example where there's pretty high concordance across both of these, except for group Y, its number 1 pick was 12, and group X, its last pick was 12. But we could go ahead and do that and then say, well, what does the Kendall tell us? Kendall tells us that that's our concordance, and we could likewise say, well, what does Spearman tell us? Which is the same as what Pearson would tell us, because it's already rank transformed. And it would give us, here a much lower value. And so the argument might be that if you're dealing with things that are inherently ranked, like rating your favorite restaurants or movies or beers or sodas or whatever it might be, that something like the Kendall's correlation might be the more appropriate test. So I wanted to present those two different Spearman and Kendall, just because they do appear quite a bit in the literature, and people use them quite a bit in various fields, especially Spearman's rank correlation. People seem to still absolutely love. Most other non-parametric tests have gone out of fashion, but Spearman, it's not dying. People like it, so I wanted you to be familiar with it. So there you have it. Those are the other kinds of correlations. All right, one last final thing to think about with correlation. And I'm sure that many of you already know what I'm going to say, because it's something that's probably been said a million times to you before. But correlation is not causation. It is very dangerous to misinterpret a correlation as describing something that is causative. One of the more famous ones is where there's a correlation and clearly no causation, are violence in Chicago is correlated with ice cream sales in Chicago. And so if it was causative, the way that you could prevent problems would be to ban ice cream, but that might result in something else bad happening. And so it's really important to recognize that when we're dealing with correlations, we're not modeling the data as a causative model. All we're doing is we're describing how things rise and fall together. It has nothing to do with causation. And I included in the R code that was posted a link to a website that basically just shows ridiculous correlations. And it's kind of fun to go through. We go through a couple of them just because it amuses me sometimes. So let's see, U.S. spending on science, space, and technology, and suicides by hanging, strangulation, and suffocation. That correlates at 99.79%. So that is a really super high correlation. That's almost a perfect one-to-one correlation, and clearly there's nothing causative between that. Number of people who drowned by falling in a pool correlating with the films that Nicolas Cage has appeared in. That correlation is 0.666. That is still a pretty darn good correlation. Again, probably not a lot of cause and effect going on there, but still a high correlation. Per capita cheese consumption correlating with the number of people who died by becoming tangled in their bed sheets. That correlation is 0.947. That is a really super high correlation, and I think that it would be difficult to kind of make any kind of causative argument about that. And so these are just kind of amusing ways in which we can convince ourselves that correlation under no situation should be misconstrued with causation. And the website has, I don't know, somewhere at the bottom or something, it allows you to kind of go through a bunch of different, you can make up your own correlations and kind of play around with it. Letters and winning word, Scripps National, winning bee, and number of people killed by venomous spiders. That is a really strong correlation. We would all feel safer playing around in dark, dank basements if only they had easier words at the spelling bee, apparently. So keep that in mind. Correlation, it ain't causation. The second thing that I want to encourage everyone to do, and we've been doing it up to this point, whenever we've played with data, either if it was real data or simulated data, one of the first things that I always do is, if it's univariate data, I'm at least going to make a histogram. I just want to get an idea of what the data look like. Is it normal? If it's not normal, is there something I can do to it so it could become normal? So that way I could use my bag of tricks from the normal distribution. And likewise, when we started playing around with correlations here, the first thing I did was I made a scatter plot just to kind of eyeball my data to get an idea of whether or not I feel good about even looking for covariance. And, as an example, and this is in the R code. Oh, I can shrink myself. I don't need to disappear way up there. I can make myself small and insignificant. There I am. So reading in these data and this is just the script that you have. We have two series of numbers. There's 142 of them, x1 and x2. And so I could look at the mean of both of those, and I could be like, okay, well, I can calculate the mean, and let's not forget what we want the mean to mean. We want the mean to mean what we want the mean to mean, which is that central location parameter from a normal distribution. And so we could go ahead and, we could plot it. Let's do that. Let's make a little plot. Let's make a histogram of x1. And we look at that, and the first thing we think to ourselves is, that is not terribly normal, not feeling too great about that. We could look at a histogram of the second variable, x2. It's like, that's not as bad, but boy, that first one, yeah, that's not normal. Now suddenly, maybe I am thinking I might have to do a Spearman rank correlation even. And we could plot out that in a bivariate plot, and it looks something like that. And so there's clearly a pattern here of like a circle where there's nothing in the middle. That's that kind of bivariate nature that we saw. Yeah, that doesn't look like that great of something we might expect to co-vary necessarily, but we could. So let's do it, because if we can, why not do it? Electrons are free. So if I were to say I want to do the correlation between x1 and x2, okay, I get a correlation of negative 0.06. So it's a pretty small correlation anyways. But that exploratory data analysis part is really important, because I have here, I'm going to pull it down because I've already plotted it. All of these bivariate plots, they all have roughly that correlation of negative 0.064, okay? And again, a correlation of negative 0.064 is probably going to be not significant, but you wouldn't want to walk away from that and say, there's nothing interesting happening with my data. Because again, this is the first group we did up here in the upper left. That's that first one that we played with. But boy, look at that. That's a perfect circle. That could potentially be super interesting. But if we just blindly followed, let's do the core test. Core.test. Oh, it's not significant. Nothing to see here. Nothing interesting. And it's like, what do you mean there's nothing interesting? Let's look at that data. Where did it go? Where did my data go? There it is. That's interesting. Certainly that's interesting. If you collected a bunch of data and you plotted it out and it looked like a dinosaur, heck yeah, that's super interesting, even if the p-value is, what, 0.4483. Too bad I have to accept the null, fail to reject the null. But wait a minute, it looks like a dinosaur. That in and of itself is worth communicating to the world. And then, these ones look like stars. These are clearly all patterns that are interesting, either because they're amusing, like the dinosaur, or the star. That's pretty amusing. But, things like this, that could be interesting biologically. Like, well, why are these doing these weird things? And why are there these clusters here? And again, you would lose all that if you just blindly followed the hypothesizing part of dealing with correlations. So always do the look-see at your data. And the fancy formal way of doing that look-see is called exploratory data analysis, which quite literally means look at your data before you start analyzing it so that you have an idea as to whether or not you're modeling it correctly, and if the type of statistical analysis you're going to do is even appropriate for it. And so on that, I will wrap this all up and say that I hope that you've enjoyed our introduction to bivariates. We've covered a lot of ground, but that's good, because starting next week, we're ready to start building real models instead of just doing statistics and making inferences based upon statistics. Next, we'll start building statistical models, and that's where the fun begins. So enjoy playing around with correlations, and we'll see you next time.